Hello everyone. Welcome to today's presentation. I'm excited to introduce our topic, electromagnetic induction. On this first slide, you'll see the title clearly displayed. We'll explore how changing magnetic fields can generate electric currents, a fascinating concept that underpins many modern technologies. Over the course of this presentation, we'll cover the fundamental principles, key experiments, and practical applications of electromagnetic induction. Let's dive in and discover the magic behind this essential physical phenomenon. Let's now look at some important concepts in electromagnetic induction, starting with self-induction and self-inductance. These refer to how a coil or circuit can oppose changes in its own current due to its magnetic field. Then, we have Lenz's law, which tells us that the induced current always acts to oppose the change that caused it. It's a fundamental principle that helps us understand the direction of induced currents. Moving on, eddy currents are loops of current induced in conductors when they experience changing magnetic fields, often causing energy losses, but also useful in devices like braking systems. Next, we delve into Faraday's laws of electromagnetic induction, which are the foundation for understanding how changing magnetic flux induces an EMF. We'll explore methods of producing this induced EMF, such as moving a coil in a magnetic field or changing the magnetic flux through a coil. We also examine mutual induction and mutual inductance, where the change in current in one coil induces an EMF in another nearby coil. Finally, we'll look at the expression for the induced EMF based on both Faraday's laws, tying everything together, and include some additional information to give you a broader understanding of these phenomena. All these points connect to the overarching theme of how changing magnetic fields generate electric currents, which is central to electromagnetism. Magnetic flux, represented by the symbol phi, is essentially a measure of how many magnetic lines of force pass through a given surface. Think of it as counting the number of magnetic field lines crossing that surface. Now, this isn't just a simple count. It also depends on the orientation of the surface relative to the magnetic field. In fact, magnetic flux can be defined as the product of two things: the area of the surface we're considering and the component of the magnetic field that is perpendicular or normal to that surface. So, if the magnetic field lines are passing straight through the surface, the flux is maximized. If they skim along the surface at an angle, the flux decreases. Understanding this concept is fundamental because it helps us quantify how magnetic fields interact with different surfaces, which is crucial for analyzing electromagnetic induction and designing various electrical devices. So, in essence, magnetic flux gives us a clear picture of how magnetic fields permeate through space and objects. Let's take a closer look at these equations. First, we have the magnetic flux, which we denote as phi. It's calculated as the product of the magnetic field B and the area A, but importantly, we also include the angle theta between the magnetic field and the normal to the surface. So the formula is phi equals B times A times cos theta. This highlights that the flux depends not just on the strength of the magnetic field and the area, but also on how the field is oriented relative to the surface. Next, we see the differential form, d phi equals B times ds. Here, ds represents a small element of the area through which the magnetic flux is passing. This differential expression is crucial when we're dealing with changing flux or integrating over a surface. Overall, these formulas are fundamental because they connect the magnetic field, the geometry of the area, and the orientation, all key factors that influence magnetic flux. Understanding this relationship sets the foundation for grasping how changing magnetic flux induces currents, which is central to many electromagnetic applications. Let's take a closer look at the different types of magnetic flux and how they vary with the angle theta. When theta is between 90 degrees and 270 degrees, the magnetic flux is negative. This means that the magnetic field lines are oriented in such a way that they oppose the direction we consider positive. At exactly 90 and 270 degrees, the magnetic flux drops to zero, indicating that the magnetic field lines are perpendicular to the surface and do not pass through it. Finally, for angles between 0 and 90 degrees, as well as from 270 to 360 degrees, the magnetic flux is positive. This shows that the magnetic field lines are aligned with our reference direction, resulting in a positive flux. Understanding these variations helps us grasp how magnetic fields interact with different orientations, which is fundamental to analyzing electromagnetic phenomena. So, when it comes to changing the magnetic flux across a coil, it can be achieved through a combination of factors. First, the area of the cross-section of the coil, which we denote as A, plays a significant role. If you increase the area, you're effectively increasing the amount of magnetic field passing through the coil. Next, the orientation of the coil relative to the magnetic field, often represented by the angle theta, is crucial. When the coil is aligned more directly with the magnetic field, the flux is maximized, and when it's at an angle, the flux decreases accordingly. Then, there's the strength of the magnetic field itself. A stronger magnetic field results in a greater flux passing through the coil. In essence, the magnetic flux isn't fixed. It can be altered by adjusting any of these factors: area, orientation, or magnetic field strength. Understanding how these elements interact helps us control and predict electromagnetic induction in various applications. Let's talk about the units used to measure magnetic flux. In the centimeter-gram-second, or CGS, system, the unit of magnetic flux is called the Maxwell. To give you a sense of scale, 1 Maxwell equals 10 to the power of -8 Weber. Moving over to the SI system, which is more commonly used today, the unit of magnetic flux is the Weber, abbreviated as WB. Sometimes you'll also see it expressed as Tesla meter squared, or TM2. Understanding these units is important because they help us quantify magnetic flux accurately across different systems and applications. Let's take a closer look at how magnetic flux linked with the coil changes as the position of the coil and the magnet varies. Essentially, the magnetic lines of force are cutting through the coil at different angles, even when the cross-sectional area stays the same. This variation in the angle affects how much magnetic flux is linked with the coil at any given moment. It's a key concept because it explains why the induced voltage varies when the magnet and coil move relative to each other. This understanding sets the stage for Faraday's experiments, where he demonstrated how changing magnetic flux induces an electric current. So, in essence, the way magnetic lines of force interact with the coil is fundamental to understanding electromagnetic induction. Let's start by looking at the key points on this slide. First, we see that the induced current, or electromotive force, is only generated as long as there's relative motion between the coil and the magnet. This means if they stop moving, the current stops as well. Next, we have the induced polarities of magnetism in the coil. This refers to how the magnetic poles appear in the coil when the flux changes. It's all about how the magnetic field influences the coil during motion. Then, we examine the direction of the current through the galvanometer, which determines the deflection we observe. The direction of the current depends on the movement and the change in magnetic flux, and this is what causes the needle in the galvanometer to deflect in a particular direction. Finally, the first point emphasizes the importance of the relative motion between the coil and the magnet. Without this motion, no current is induced, highlighting the fundamental principle behind electromagnetic induction. Throughout this experiment, these observations reinforce the core idea that changing magnetic flux through a coil produces an induced current, but only when motion is involved. It's this dynamic interaction that drives the whole process. When the primary circuit is open, the current starts to decrease from its maximum value down to 0. During this process, the changing current creates a changing magnetic flux across the primary coil. This magnetic flux is linked across the secondary coil, which then induces a voltage, or electromotive force, in the secondary coil. It's this changing magnetic flux that's key to inducing current in the secondary coil. Now, when we close the primary circuit, the current begins to grow from 0 up to its maximum value. As it increases, it again causes a changing magnetic flux in the primary coil. Since this flux is linked to the secondary coil, it induces an electromotive force there as well. So, whether the current is decreasing or increasing in the primary, the change in magnetic flux is what drives the induction of voltage in the secondary coil. This entire process highlights the fundamental principle of electromagnetic induction, how a changing current in one coil can induce a current in another coil through the magnetic flux linkage. It's a core concept that underpins transformers and many other electrical devices. Whenever there is a change in the magnetic flux linked with a circuit, an electromotive force, or EMF, is induced. This EMF causes a current to flow in the circuit, but it's important to remember that this induced current only lasts as long as the magnetic flux is changing. Once the flux becomes steady again, the current stops. This idea is fundamental to Faraday's laws of electromagnetic induction, which we'll explore further. It highlights how variations in magnetic flux are directly responsible for inducing currents, a key principle in understanding how electric generators and transformers work. So, in essence, whenever the magnetic environment around a circuit changes, it creates conditions for current to be generated, tying into the broader theme of how changing magnetic fields produce electrical energy. Let's take a closer look at this second law of electromagnetic induction. The equation E equals K times d phi slash dt shows us that the induced EMF, or electromotive force, is directly proportional to how quickly the magnetic flux, phi, changes over time. In simpler terms, the faster the magnetic flux linked with a circuit changes, the greater the induced EMF will be. This means that if you have a rapid change in magnetic flux, you'll generate a stronger induced EMF, which is the core idea behind many electrical devices like transformers and electric generators. The key takeaway here is that the magnitude of the induced EMF depends directly on the rate at which magnetic flux varies. So, as we move forward in understanding electromagnetic induction, keep in mind that it's not just about having a magnetic field, but about how quickly that magnetic environment is changing around a circuit that really drives the EMF generation. This principle ties everything together in how we harness magnetic fields to produce electrical energy efficiently. The direction of the induced EMF or induced current is such that it opposes the change that is producing it. This is a key concept in understanding electromagnetic induction. Essentially, when a change occurs, like a magnetic field increasing or decreasing, the induced current acts in a way that tries to resist that change. It's almost as if nature is trying to maintain a sort of balance. This idea is captured beautifully by Lenz's law, which states that the induced current always flows in a direction that opposes the cause of its creation. And what's really important here is that this behavior aligns perfectly with the law of conservation of energy. In other words, Lenz's law ensures that energy isn't created or destroyed. Instead, it's transferred or transformed in a way that maintains the overall energy balance. So, this law not only helps us predict the direction of currents, but also reinforces our understanding of fundamental conservation principles in physics. Let's take a closer look at the expression for induced EMF. As you can see, the formula is E equals negative N times d phi over dt. This tells us that the induced EMF depends on how much magnetic flux is changing with time. The negative sign here is crucial because it represents Lenz's law, which states that the direction of the induced current opposes the change in flux that caused it. When we simplify the formula for a single loop, it becomes E equals negative d phi over dt. This version makes it clear that the EMF is directly related to the rate of change of magnetic flux. By understanding these expressions, we're seeing how both Faraday's law and Lenz's law work together to describe electromagnetic induction. They show us that any change in magnetic flux, whether through a coil or across a surface, generates an EMF that opposes that very change. This concept is fundamental because it links the physical change in magnetic flux to the electrical response in a circuit, helping us understand how transformers, electric generators, and many other devices operate. Now let's look at this important equation. I equals negative d phi divided by r times dt. This tells us how the induced current relates to the change in magnetic flux. What's really interesting here is that the induced EMF, which is this negative rate of change of flux, doesn't depend on the resistance at all. Instead, it's determined solely by how quickly the magnetic flux changes. However, when we talk about the actual induced current and the charge that flows, these do depend on the resistance. The resistance essentially acts as a limiting factor, influencing how much current can flow for a given EMF. So, in essence, while the EMF generated by changing magnetic flux is independent of resistance, the resulting current and charge are affected by it. This distinction is key to understanding how electromagnetic induction works in real circuits, especially when considering energy transfer and circuit design. All right, let's take a closer look at this equation. The rate of change of charge, dq/dt, is equal to negative the rate of change of magnetic flux, d phi, divided by r times dt. Essentially, this formula describes how charge varies over time in response to changes in magnetic flux. The negative sign here is important because it reflects Lenz's law, the idea that the induced current opposes the change in flux that created it. When magnetic flux increases, the induced charge change acts in a way to oppose that increase, and vice versa. This expression is fundamental because it connects electrical quantities like charge and current directly to magnetic phenomena, showing the deep relationship between electricity and magnetism. It's a key piece in understanding how electromagnetic induction works, which ties into the broader theme of how energy and fields interact in electrical systems. Now, let's look at some of the ways we can change the magnetic flux, which is key to inducing EMF in a circuit. First, magnetic flux, represented as phi, can be altered by changing the relative orientation of the loop with respect to the magnetic field, B essentially. By rotating the loop, we change how much of the magnetic field lines pass through it, which directly impacts the flux. Next, another method is by changing the area of the loop itself. If we increase or decrease the area A that's exposed to the magnetic field B, the flux changes accordingly. This variation in flux influences the induced EMF, making it stronger or weaker depending on the size of the loop. A third way is by modifying the magnetic field B directly. If we increase or decrease the strength of the magnetic field acting on the loop, the flux through the loop changes as well. This method was actually demonstrated in Faraday's experiments, showing how varying the magnetic field induces EMF. So, to summarize, there are three primary methods for producing induced EMF: changing the relative orientation of the loop, altering its area within the magnetic field, and varying the magnetic field itself. Each of these methods affects the magnetic flux in a different way, but all lead to the same fundamental phenomenon, inducing EMF in a circuit. Eddy currents, also known as Foucault currents, are essentially loops of electrical current that are induced within a solid metal when there's a change in the magnetic field around it. These currents circulate within the metal itself, kind of like tiny whirlpools of electricity. They are produced whenever the magnetic flux, that's the magnetic field passing through the metal, varies over time. This change in magnetic flux causes the electrons inside the metal to move, generating these circulating currents. Understanding eddy currents is important because they can have both useful and unwanted effects in various applications, which we'll explore further. Now, let's look at some of the key applications of eddy currents and how they are utilized in various fields. First, eddy currents are used in diathermy for localized heating of tissues, which is particularly useful in medical treatments to target specific areas without affecting surrounding tissues. Next, in the context of railways, electric brakes on trains rely on eddy currents to help halt the rotation of the axles, providing smooth and efficient braking. In speedometers, eddy currents are employed to measure the instantaneous speed of a vehicle, offering real-time feedback for accurate speed readings. Energy meters, or watt meters, also use eddy currents to measure electric energy consumption, making them essential for billing and energy management. Additionally, deadbeat galvanometers utilize eddy currents to quickly stop the damping of the coil, which improves their precision in detecting tiny currents. Finally, eddy currents play a role in induction furnaces, where they are used to melt iron ore efficiently, facilitating the steel-making process. These applications highlight how eddy currents are integral to both industrial and everyday technologies, showcasing their versatility and importance. Self-inductance is defined as the magnetic flux linked with a coil when a unit current flows through it. Think of it as a measure of how much magnetic field is generated by the coil per unit of current. Now, when we talk about self-induction, we're referring to the phenomenon where an electromotive force, or EMF, is induced in the same coil due to a change in its own current. This change in current causes a change in magnetic flux within the coil. What's really interesting here is that this induced EMF opposes the change in current, so it acts like a kind of resistance to sudden increases or decreases. This opposition is what we call self-induction. It's a fundamental concept because it explains why current doesn't just change instantaneously when we switch things on or off. By understanding self-induction and self-inductance, we see how coils can resist rapid changes in current, which is crucial in designing transformers, inductors, and many other electrical devices. It ties into the overall theme of electromagnetic phenomena and how magnetic fields interact with electric circuits. Now, let's look at mutual inductance. It is defined as the magnetic flux linked with the secondary coil when a unit current flows through the primary coil. Essentially, it measures how effectively the primary coil can induce a magnetic flux in the secondary coil. Mutual induction, on the other hand, is the phenomenon where an electromotive force, or EMF, is induced in the secondary coil due to a change in current in the primary coil. This change in current causes a change in magnetic flux in the secondary coil, which is the core idea behind mutual induction. So, when we talk about mutual induction, we're really describing how a varying current in one coil can influence another nearby coil through their magnetic fields. This concept is fundamental in understanding how transformers work and many other electrical devices. In summary, mutual inductance is the quantitative measure of this coupling between two coils, and mutual induction is the process that enables energy transfer between them via changing magnetic flux. This connection highlights the importance of magnetic fields in electrical engineering and the way we transfer energy efficiently in various applications. When we have two solenoids wound on a magnetic core with a relative permeability, or μ, the formula for mutual inductance needs to be adjusted accordingly. This means that the magnetic properties of the core influence how effectively the magnetic flux links the two coils. The coefficient of coupling, which we denote as K, is defined as the mutual inductance, M, divided by the square root of the product of the self-inductances, L1 and L2. This coefficient essentially tells us how well the two coils are coupled magnetically. Typically, K is less than 1, indicating that perfect coupling is rarely achieved in practical scenarios. Understanding this relationship is key when designing magnetic circuits and transformers, as it helps us predict how energy transfers between coils and how efficiently they operate together. This concept ties back to the overall theme of magnetic coupling and the importance of core materials in optimizing inductive components.